Welcome back Year 12 to this series on circular functions. In this video, we're going to look at graphing the tangent function. This exercise in the Cambridge textbook also covers trigonometric equations involving tan. Since we covered those in class already, I'm not going to cover it again. We'll just focus on tan graphs in this video. So I'd like to begin with a geometric definition for the tangent. Previously, suppose we had an angle theta measured counterclockwise from the positive direction of the x-axis on the unit circle. If I draw a point, if I label the point which makes an angle theta counterclockwise lying on the unit circle, that point has coordinates cosine theta and sine theta. Now, if I extend that line further out until x equals 1, it intersects the line x equals 1 by definition at the point 1 tan theta. So I have a situation involving similar triangles like so. So first, for the first triangle, it's cos theta, sine theta. And for the second triangle, it's 1 and tan theta. And depending on how much maths you've done in the past, one thing you might know is that if I take the ratio of the vertical lines and the horizontal lines, I get the same, I should actually do it like this. So 1 for cosine and one for the shorter triangle and one for the longer triangle. If I take those ratios, I get the same thing because I kept the angle the same, theta. So I can write this. Sine theta divided by cosine theta is the same as tan theta over 1. And rearranging this equation, I get the definition, which I presented in class. Tan theta equals sine theta on cosine theta. And that's something that you should have memorized in this class. Please note that if cosine is 0, so that is pi onto 3 pi onto plus n pi, where n is an integer, then tan is undefined. It goes off to positive infinity or negative infinity. And that's why if you try tan of 90 degrees on a scientific calculator, it returns a math error. So that's the definition for tan. And now the question is, what happens if I apply this definition and graph it for different values of theta? This one is not as easy to do as it was for sine and cosine, because there we could just consider x and y coordinates on the unit circle. Here we actually have to take the ratio. So what I'm going to do here is I'm just going to show you the shape of the graph. And we'll start with tan x. So the simplest possible version, there's no dilations, translations, or reflections. So first thing to note is that tan of x passes through the origin 0, 0, and that's because sine of 0 is 0, and so the numerator of tan will be 0. As the angle increases, we get the following happening. So tan increases, and then it goes off to infinity like this, and in the opposite direction it does this. So at 0, 0, and it has it's called a point of inflection. You'll learn more about what that means when you study calculus. Essentially, the gradient function or the derivative has a turning point. However, it's not stationary. So you should not draw a flat line at the origin. you'll see how my graph is sort of angled like this. That's because it should be like that. Now, there are asymptotes. The first place where tan is undefined is at pi on 2. And then the next angle is 3 pi on 2. And similarly, if I go in the opposite direction as well. Now, one more thing I want to say at this point is, just like with sine and cosine, there was periodic behavior. As I made my way around the unit circle, the graph repeated. Same thing happens for tan. In fact, if you study the unit circle carefully, you'll see that tan repeats every pi radians rather than 2 pi, because tan is positive in both the first quadrant and the third quadrant. So I get a repeating pattern twice as often compared to sine and cosine. So you'll see these asymptotes, negative pi on 2 and pi on 2, they are spaced pi units apart. And then to go from pi on 2 to 3 pi on 2, it's another pi units. So once I've drawn one cycle of the tan, I can do the same thing like this. So this one's going to be the point pi 0, because I've gone across pi units from the origin, and then it'll also go through negative pi 0 as well. Now, we're still missing something here because we don't have a sense of the vertical scale. What I need to label is a really convenient point where tan is known. And the simplest possible one that I could choose is halfway between 0 and pi on 2, which is pi on 4. From previous studies, you know that tan of pi on 4 is just 1. So that's actually the easiest value to label on this graph. And now I can tell the period and the vertical scale from looking at this graph. So now I have a complete graph showing 3 cycles of tan. And if I wanted to, I could continue to extend this graph as far as I wanted to. Okay, so what have we learned? We've learned that the graph of tan has period pi rather than 2 pi, so please note the difference there. And the asymptotes were at plus or minus pi on 2, plus or minus 3 pi on 2, and I just keep adding pi units to the left or to the right. Okay, and it goes on forever. Now, some books, I think including our textbook, they like to sort of wrap up all of these asymptotes using a parameter. It's all the odd numbers divided by 2. So what we can do is we can use the number 2n plus 1 pi divided by 2. So 2n will give me all the even integers, and 2n plus 1 will give me all the odd integers. So just remember, z means the integers. Okay, now let's consider tan of n times x. So now I have a coefficient in front of x. What that's going to do is it's going to dilate by a factor of 1 on n from the y-axis. And here I'll just assume that n is positive. Okay, so if I have, say, tan of 5x, that's going to shrink my period from pi to pi on 5. It's going to get shorter. So tan nx will change the period from pi to pi on n. And now my asymptotes will be shrunk by a factor of 1 on n. So instead of pi on 2, it'll be pi on 2n. Instead of 3 pi on 2, it'll be 3 pi on 2n. Instead of 5 pi on 2, it'll be 5 pi on 2n, and etc. And again, if I want to encapsulate all of these asymptotes into one family, I could use x equals plus or minus I just realized I've used n twice. So what I'll do is I'll change this to k. And then now I can divide everything by n. So 2k plus 1 pi divided by 2n, where k is an integer. Okay, I don't know whether you would memorize this, but I think this is something that you'd be able to derive on the spot because you would know, by the end of the year, you will know this. You'll know that tan has period pi and that there's asymptotes at pi on 2. And then from that, you can deduce the rest of this page. Okay, so let's finish with a couple of examples. Again, this time I'm going from a graph to an equation. So here we have part of a tan graph. I've deliberately drawn it away from the origin to focus your attention on particular features of the graph. So what will we do? Well, we would start by writing down the period. In this case, it's the difference between 15 and 5, because that's one complete cycle. Remember, one complete cycle is between two adjacent asymptotes. So the period is 10. If I were to draw another cycle, the halfway point would be at the origin. So no horizontal translation is needed. However, you should notice that this is actually opposite to the way we drew the tan graphs earlier. So we could capture this with either a vertical or a horizontal translation. Sorry, a vertical or horizontal reflection. And it doesn't matter because they're actually the same, since tan is an odd function. So this time, if I define y equals a times tan of mx, my period is going to be pi on n instead of 2 pi on n. So pi on n is 10, which means n is pi divided by 10. So now I've got a situation where y equals a times tan of pi on 10x. And now I need to substitute a coordinate to find a. And because of the reflection, I'm expecting that a is going to be negative. So let's see if this happens. Let's substitute 7.5 and 5 into this equation and see what happens. So we have 5 equals a times 10 of 7.5 on 10 is 3/4, so it's 3 pi on 4. And tan is negative in the second quadrant. So tan of pi minus pi on 4 is the same as negative tan of pi on 4, which is negative 1. And therefore a is negative 5, as we expected. And so my final equation is y equals negative 5 tan of pi on 10x. And we're done. The reason why the next branch of the tan graph on the left passes through the origin is because the period was 10. If the period wasn't 10, then we would need to do a horizontal translation. Finally, I just want you to remember I needed to use this point to define the vertical scale of the graph, which was captured in that value, capital A. All right, last example. Okay, so this time I've given you, just notice an error here, so I'll just change that. So I've said that the graph passes through 1, 0, and that the graph goes from x equals 0 to x equals 2, and these are asymptotes. Okay, so this time a horizontal translation is needed, because remember, the original tan graph looked like this. At the origin, we had a point on the tan graph, whereas here, in this particular graph, we have an asymptote at x equals 0, which means the graph has been shifted. So we'll need to work out how much to shift it by. And I think the easiest thing to do first is to find the period. So here the period is 2. Since adjacent asymptotes are separated by an interval of 2, and that means pi on n is 2, or n equals pi on 2. Our general equation will look like this. It'll be some dilation factor from the x-axis, giving me my vertical scale, times tan of n with some horizontal translation. And here there's no vertical translation needed because the x-intercept is halfway between the asymptotes. So if that happens, no vertical translation is required. However, if the x-intercept wasn't at 1, that is, it wasn't halfway between 0 and 2, then I would need to consider a vertical translation as well, which I could capture with this. But for now, this is all we need. Now, the question arises, how much do I need to shift it over? If you think about it, if my original graph looks like this, with the asymptote sort of at negative pi on 2 and pi on 2 for tan x, if I shifted it to here, I would need to shift it pi on 2 units to the right. Specifically, I will need to shift it half a period. So we're going to translate half a period. Now, again, because tan is an odd function, it doesn't matter whether I translate it to the left or to the right. In this case, I think it makes sense to translate it to, oh, hang on, does it matter? In this case, it doesn't matter because the asymptote is exactly at x equals 0. If it wasn't exactly at x equals 0, then it would matter. So I'll just say to the right or to the left by symmetry. So we'll translate half of 2, which is 1. And that means my equation is now y equals a times tan of pi on 2, x minus 1. Now, if I substitute x equals 3 on 2, I get tan of 3 pi on 4. I get tan of pi on 4 because 3 on 2 minus 1 is a half. I'll write it out for you, just because I think it's going to be easier to follow. Okay, so substitute x equals 3 on 2 and y equals 3 to find capital A. 3 equals a tan of pi on 2 times 3 on 2 minus 1. 3 equals a times tan of pi on 4. A equals 3, since tan of pi on 4 is 1, and therefore y equals 3 tan of pi on 2 times x minus 1. And that, my friends, is the tan graph. If you wanted to add another layer, you would add a vertical translation as well as a horizontal translation but it's the same thing. You would just need plus k at the end of the equation, and you would need an additional coordinate, most likely, per cycle. That should be enough to get you going with tan graphs, and look forward to seeing you in the next video. Thanks.